Yeah, so yesterday we stopped at this idea that even though we have this generic notion of negation that allows us to say that it's not the case that A implies B, for
You're not
instance.
actually projecting.
Oh, sure.
You need to
It
pick
is on.
HDMI.
Oh,
You either need to pick HDMI or you need to plug the USB-C in.
oh, and I.
It's going. It's doing it. It's doing it.
Yeah.
You're there.
So even though we can use this notion of negation to express the idea that it's not the case that A implies B, there are actually better definitions than that give you more information. So this was this idea, for instance. So not implies is taking two sets and giving you a set. And the idea is that you're going to combine both evidence that A is inhabited, because if A is empty, then we know for a fact that you will always be able to write a function from A to B by the principle of explosion. So some more evidence is like, I could actually give you an argument to proceed with A implies B, but then your claim that you will be able to prove B is nonsensical. And so you could, when you're building like a proof of a negative statement, instead of using nots, define your own like personal definition, which gives back more information.
Yeah.
But to formulate this, we actually need to explain what it means to have both A and not B. And so far, we've not defined conjunction. But I don't think it will be a huge surprise to you that we can define conjunction. So it's characterized by this main rule. I mean, there's also an elimination rule, but
just to check, in your experience, have you encountered logical rules being presented this way as a kind of giant fraction, where there's a line which separates assumptions above and conclusions below? So this rule says, they're always better read from bottom to top. It says, if you're in the business of proving A and B, then you use this rule to split that up into the job, prove A, prove B. So always read from the bottom up, because they're always saying, if this is your problem, here's how you make progress.
Right, and I did it, of course, exactly the other way around.
Yes.
So
Or
if we want to prove this, it's enough to prove that. Or to prove these, I guess.
yes,
Those.
yes.
Okay. But it sort of goes both ways. It's also the case that if you've accumulated some evidence for various things, you can package it up as evidence for the conjunction of both of them. And we actually saw something like this last week, I think. What were we doing? We wanted to return. Oh, it was the unsplit.
Yeah.
No, the split.
We were
unappend
We're chopping
on vectors, right? So we were taking a vector whose length was known to be of size m plus n, and then we're saying we're going to give you both the prefix of size m and then the suffix of size n. And that's the same idea, right? When you want both things, you can say, I want a type. And that's going to be parameterized by these two sets for A and B, and itself it's going to be a set.
Do you want it to be called AND, or do you want it to be called some infix wedge symbol?
I can, whatever. I mean, we can use more Unicode. I was trying to be nice to you, but
well, no, I'm just noticing that you've used it everywhere.
Well, not later in the file, I think, but
okay.
yeah. And so we're using a record because there's only one way to build such a thing, right? It's by combining a proof of A and a proof of B. And then we can say the first proof will have type A and the second proof will have type B. And maybe I should give us a constructor for it.
That might be nice.
So I'm going to call it comma, if I can type it. Because just like the pair we defined a week or two ago, it's literally just a pair of things. We can define the diagonal. Oops. Let's do it like this. So what's the diagonal? It's proving that if you can prove A, then you can prove A and A. And hopefully that's not controversial and Agda can find it automatically. And then something slightly more interesting, swap. If we know that both A and B are true, then it should be the case that B and A are true also. Okay.
You have
Variable
yes.
B. Okay. And let's do it the nasty way. So
Yes.
Agda is able to figure it out because, I mean, there's a single definition anyways. You can see that it's somewhat nasty.
Do you want to do an open on that
Yes.
thing?
So here we're using the fully qualified names because I haven't opened the module. So whenever you define a record, it comes with a module definition that has exactly the same name. And these projections are only in scope in that module. But just like any other module, you can just open it.
So the point there being that you might define a load of different record types that have components with the same name. And if you chose to bring them all into scope, you'd have a name clash.
Yeah.
So there's always an unambiguous way of talking about them. And if you're happy that you don't need to name the record type to do the disambiguation, then you can open it, and that just brings them into scope without any qualification. What's happening there is that second and first now make sense without being and second and first.
So it's this idea of if I can prove A and B, then first gives me the proof of A, right? So from A and B, I can derive A. And second is the other way around. But you could also proceed differently. You could say, let's do it like this. Well, there's only one way you could have proven this A and B. It's by building a pair. So you could take the pair apart, extract the A and the B, and then hopefully, yeah, there we go. Agda is able to figure out that then the B flows to the first position and the A to the second one. And I won't say the third one, maybe I'll do the third one too. So lastly, and this is only for records, we know that records are only ever constructed with, oops, terrible naming as always. They're constructed by basically putting together the value of all of their fields. So one other thing you can do is say, well, instead of using the constructor and then explaining how things are going to fit together, I can explain field by field what I want. So here, if I do a case split on nothing at all, it will introduce, okay, that's
kind of ugly, but never mind, eh?
The version I like. There's so many ways to write this code. It's ridiculous, but this is the version I like. So I'm saying I'm going to build a pair here of B and A. And first, I'm going to explain what the first projection of that pair is, and that's B. And then I'm going to explain what the second projection is, that's A. So just like data is always built with constructors, morally records, they are built by explaining how you can project out of them. It's just that here we're doing all at once, and here also. But here we're decorrelating each of the fields.
So there's an interesting escalation with these three different proofs. Because pragmatically, what's important is when you switch from working on the left-hand side of the program to working on the right-hand side of the program. So in the first definition, we go over to the right-hand side of the equal straight away. We're not using even the ability to name the inputs on the left-hand side of the program. We're jumping straight in there and say, I'm going to just tell you what the output is. I'm just going to build it. Once we start building stuff up with that lambda, we are committed to our current state of knowledge. We've stopped looking and we've started making. So if we regret and want to look a bit more, too late. Whereas in the middle one, we do a bit of looking. We've got something on the left-hand side. We're taking it to pieces. We're making the problem simpler. And then when we're ready to build the pair on the output, that's when we cross the equal sign and start building stuff up from the pieces that we picked out. And this is the extreme version, where we stay left as long as possible, where we say, yes, I'm going to look at the input. Yes, I'm going to make the output a little bit at a time. You know, if there was more stuff to pattern match on here or whatever, I still could. And it's only when I absolutely have to give the individual pieces of the output that I move to the right of the equal sign and say, okay, this is what it is. So this is a very important pragmatic thing about programming in Agda. A lot of the time, you find yourself needing to think, how do I stay on the left for as long as possible? Because you've got more freedom to find stuff out when you're on the left. So that's a key example, actually. And this ability to build records by one field at a time and stay on the left is really useful.
And I think we have a concrete example coming up immediately.
Cool.
So now we are able to define our notion of not implies because we have conjunction, and we can prove. Okay, yeah. So it's not, isn't it? Not implies. Took. And maybe you want to do it, staying on the left as long as possible.
Uh-huh. Yeah. Okay. So
wait, can I forgot. Yeah, if I throw in an option at the top, it might not generate the nasty right. Options, postfix projections.
Let's see how we do. Okay.
I'm hoping it will be nicer this way.
So, can we make the font in the info buffer slightly bigger? What's your make big? Okay, good.
Yeah.
Right. Okay. So, I look at the goal. It doesn't expand the definition, so I say Control U, Control U, Control C, Control comma, because I want to see what it really means. And it's this AND thing. Okay, so I'm going to say, I want to build this up component by component, and I want to stay on the left. So I say Control C, Control T. It says empty for split on result. Split on result means component-wise. Yes. Yes, indeed. Okay, so there's another marvelous thing. Back in the Haskell world, oh no, I'll do that in a minute. Okay, so here, first goal, can we prove 0 equals 0? I think we probably can. And indeed, Agda can do it too. Right. So now we have to prove not false, which is, you know, I'm optimistic about. Right. And if I normalize that, I see that's really false implies false. Okay, staying on the left as long as possible. I'll have the assumption of false as an input, please. And so you notice that that these definitions are being used at different arities, right? You know, I see an extra input. I'm allowed to pull it to the left of the equal sign. Sorry, pull it to the left of the equal sign. You know, there's no expectation that all the clauses of a function have the same number of things in them. If the type makes sense, it's fine. Yeah, so that's a sort of artificial rule imposed in Haskell that we can and do live without. Okay? So here I've got a goal of false, I've got an assumption of false, and I'm not even looking at the goal. I'm just seeing I've got a false assumption. I'm going to stay left and tell that assumption to go away. So never had to, in the second case, we didn't have to go to the right hand side of the equal sign at all. We made the assumptions go away. So that we're really exploiting the fact that we're staying on the left, we can do more pattern matching. And here, when you pattern match, you win.
Mm-hmm. And so this is the top level equivalent to the absurd lambda that we've seen so far, right? In the absurd lambda, it's similar. You write lambda, and then this pattern telling Agda where the absurdity is. And you don't need to write right arrow and then give the body of the lambda, because you're never going to enter that lambda anyways. And here it's similar. You can just leave out the equal and the right-hand side of the definition entirely, because you know that this case is just impossible. So you're never going to use it.
Yeah, and with apologies, because, you know, over the past few years, we've taught you C, we've taught you Haskell, languages where an empty set of parentheses means something trivial.
Ooh.
And here, an empty set of parentheses means something impossible.
No. And unfortunately, that's part of the syntax we cannot change. So.
Yeah.
So we've seen conjunction, so it only seems natural to do disjunction. Now, I don't have an introduction rule for this for some reason. So it's corresponding to this idea that how do I prove A or B? Well, if I have a proof of A, I'm happy. Let's make them a little bit less wide. But then I'm also happy if I have a proof of B. So
Yeah,
I
mean, of course,
either of these situations.
Of course, what we're not happy about is, like, if our goal is A or B, this is the point where we have to make a decision. And sometimes these decisions are hard to make. And it's kind of like, before we make this decision, we want to make sure of the facts. Right?
And in classical logic, you also have like an extra axiom telling you like this out of nowhere. But of course, it's not very satisfactory for us, because then we don't know which branch the evidence came from. Is it A? Is it not A? We have no idea. And so we cannot proceed from there. So we're just going to not have this rule, and instead have this thing where every time you're making a claim, you actually have to back up that claim with some evidence.
Yeah, so here, right, the point is that you have to, what this is really saying is that we start by ponying up one bit of information that says which way we're going to go. And the thing that says, you know, B or not B, see, brush up your Shakespeare, choose B. Yes. B or not B. That is implicitly promising us a bit. I mean, it's saying no matter what the hypothesis is, we can get the bit of information that tells us whether it's true or false. That is just too magical.
So here we have two ways to build this kind of evidence. So we can't use a record anymore. Now there are multiple possibilities, but luckily we have inductive definitions, data definitions, and so you'll recognize this either from Haskell, maybe, where you're saying I can, in left, let's call it in left, A or B, and right, B.
Yeah, good old Irish National Liberation Army and the Irish National Republican Brotherhood.
Okay. And so these correspond exactly to these two introduction rules, right? And then we can prove distribution. I'm going to need to add another variable. Distribute. Okay. Let's just copy paste this thing. And I mean, we've seen this one in 106 too, right? This idea that conjunction and disjunction behave the same as multiplication and addition.
I just spent the last 2 hours teaching the first year this.
Okay. So what do? Well, we just split on the goal. Okay, it was a function, so introduce some arguments. Let's try to split on the goal again. Oops, bad idea. So here it's when it's prompted and it doesn't know what to do because there's nothing else to split on the goal, it's going to start introducing all of the implicit arguments, which is sometimes what you want, but often is not what you want. So here I try to split on the goal, but the goal is disjunction. And there's no one way to build the disjunction. You actually have to make a choice. You have to like choose that bit of information. So maybe I could even write it like this. Oops.
Yes. So yeah, don't commit too early.
So I could either go left or right, but that doesn't really make sense because I don't actually know whether my assumption is built using left or right. So the next move is to start looking at your inputs. So if you take X apart,
it uses terrible names.
B or C. Okay. So now I had A and B or C, which means I'm entitled to having both of them. And then here I have B or C, and finally I'm going to get a source of bits to actually produce the decision that I need to produce on the right-hand side. So I can look at what decision was made on the left-hand side, and either I got a P, a B, or I got a C. And now I'm basically going to replicate the choice. I think I can even probably do this. We've done enough analysis that there's a single solution now, and I can just build the term for us because it's kind of boring. The crux of it was to get to that information, which then allows us to say whether it's this B or this C that we're going to decide to prove. Truth. Do you want to do truth?
Maybe.
Maybe.
Okay. Right. So we want the type of. So we need. It's useful to have a type which represents boring information. And there's a couple of ways we could do it. So I'll look at 2 ways. What I'm going to do is I'm going to select that, and is it copy is Control C?
Alt W.
Alt. Okay, yes, we're there. It's right. So one thing I could do.
Well, the first thing you could do is we could use NAT, because NAT is always true, for instance.
Yeah. Right? But it's slightly too interesting. We can think of lots of ways of making numbers, right? You know, there's actually information in there. You know, is our proof 3 or is it 17? I want to make sure that the proposition that just says true is as boring as possible. So I could say data true, and I'm going to call this true D for data, is a set where dull is in true D. So yeah, there we go. It's definitely true because there's one proof of it. That's as many proofs as we need. You know, there are no surprises, right? You know, what is the proof of true? Do you even need to ask? So it's the sort of thing, you know, if your goal says true, you win. If you've got an assumption that says true, it's absolutely nothing to get excited about. You know. Okay, so But here's the thing. You know, we might think, okay, there's only one proof of true, so they better all be the same. A and B in, what happened there? In true D implies, do we have equality?
Yes.
Good. B, same. A, B equals what? Okay, so I might think, well, there's only one concrete value that A and B could possibly have. So dear Agda, please, will you believe me when I say that's REFL? And Agda says, well, they sure don't look like the same variable to me. If I want to do it that way, I have to say, look at this boring thing, and look at that boring thing, and now they're bloody well the same. Okay? So, that's too much of a rigmarole for something that's supposed to be this boring. So I'm going to define it not as the data type with one constructor, but as the record with no fields. To build a record, you have to fill in all the fields. And that's really easy if there's none of them. I'm also going to give it a constructor, which I'm going to call that thing, but your mileage may vary. So now I can say same prime for all A and B in true, A is B, same prime A, B equals, right. So in Agda, unless you ask otherwise, especially, Agda says two records are equal if they are equal field by field. Instead of just comparing the records themselves, it takes all the projections and lines them up against each other. So what happens when I say REFL here is that Agda says yes. Because field by field, A and B are the same. They agree on all none of their projections. So this is convenient when you can get it. It means that that there's nothing to be done. And in fact, let's even have a go at this. Let me see if I can do enough Unicode. Right. So when you write an underscore to say, I don't care what this is, you figure it out. Agda does something pretty cunning. You can see, no yellow. I just wrote underscore. I said, don't care. You figure it out. So Agda goes, I've got to figure out true and true and a record. I'm going to figure out the record one field at a time. Can I figure out the first field? That's true. It's a record. I'm going to figure out one field at a time. Oh, I already have. Now I have to figure out second. Oh, that's true. I'll figure that out one field at a time. Oh, I win. Right. Yes?
How does that differ from the way we define the entity type?
Right. So this is, so things are the other way up, right? But it's a good question that, so data are all about the choices of the ways you put things together. So if you're saying there's no way to make it, then it's empty. Whereas records are defined by the ways you take them apart. And here we're saying, well, there's nothing to see here. So the data type with no constructors gives us the empty type, gives us false. The record with no fields, right, is it's really easy to build, but it's really boring to make use of. So they're the other way up. Data is about choices. Data is a big or thing, and records are a big and thing.
And crucially here, there is a constructor.
Yeah.
Right? So
Yeah. An easy way of making it, and but it's no use to us.
So I have more examples of eta, actually.
Yes.
Now that we're on the topic, that's perfect. So we have eta for functions also. So if I have a function called f from A to B.
We should explain what we're going on about with these here Greek letters. In fact, it might be.
Well, I might.
It might be. So, when the lambda calculus was very, very young, they said there are three things that make sense to do with terms in the lambda calculus. One is that you can change names as long as you do so consistently and don't introduce a clash. Like that sort of thing. And this is called alpha equality. The names nothing has been changed except the names. Then there's the thing that actually does the computation, right? Where you've got lambda x dot t, and it's actually applied to something. And that's equal to t with s substituted for x. That's beta equality. And then I don't know why they skipped a few Greek letters. Somebody in the world will know the answer to this question. But if you've got a function, let's do it this way around. Lambda x dot f of x, where x does not occur anywhere in f, then that's just the same thing. The function which does f to its input is f. You know, and this is known in the business as beta equality. You know, life is insufferable without these two. Life gets slightly more convenient if you also have this one. And what we're saying, and the same thing happens for pairs, right? If you want to say, if I've got some pair and I take its first projection and I pair it up with its second projection, that's taking it apart and putting it back together again, right? That's the same thing. So this is what's called the eta rule for pairs. And lots of types have an eta rule. Data types in general don't have very nice eta rules, so you get no chance. But for records, to say a record is made by collecting its projections, collecting its fields. That's useful for this to be just true, and it's useful for this to be just true as well. So Agda is pretty generous at giving you these kinds of equations whenever they're straightforward.
So when you're building a language, it's always a balancing act between giving you as much of these as possible and still like keeping the compiler working. So you could decide to throw in all sorts of extra equations that would be really convenient to have, but are just undecidable. And then when you're trying to check whether a program makes sense, you just cannot, because you cannot decide whether two things that are meant to be equal are equal. These things are quite powerful already, but still manageable from the automation point of view. So that's why we try to have them in languages. So here, even in the, okay, maybe if I don't simplify it. Really?
It's refusing.
It's just refusing to see the difference between the two of them.
Yeah.
It's proactively reducing this thing even when I'm telling it, do not simplify anything whatsoever.
Yeah.
It's just very eager to simplify the representation. So that's eta for function, and then eta for pairs, as Connor was saying. So how could I write this? Let's do it with a concrete example. So if I have a pair A and B, I can say that double swapping P is the same as P. And if you think about it, right? Well, hopefully it's the version of swap that's implemented the right way around. Yeah, so it's this one. So it should just be true, I think, by normalization. Yes. So here it's not actually contracting it. I don't know why. But for records, it's not actually doing it.
Yeah.
But if you double swap, you're building the pair where the first projection is the second projection of the swapped version of P, which is to say it's the first one. And the second one is the second one. And so now if you just use REFL, because both of these are records, it's like, well, on the one hand side, on the left hand side, I have a constructor. On the right hand side, I don't have one, but I can just expand this right hand side into being the constructor with the collection of the fields, because I have a name for each field, so I can just use these names.
Yeah, it should work with swap prime as well, though, shouldn't it?
Yeah, we can try. So maybe I'll call this one swap prime. Yeah, boop, boop. Yeah,
Yep.
okay.
And the reason for that is that although it looked like we did pattern matching, that's actually behind the scenes translated in terms of taking projections. So it is the same program.
And we can do even worse. So that's function base. So we saw identity and composition. And now I can even get rid of this. Or am I gonna get? And this is one of the rare cases where you actually get to have a proof of equality between functions that looks quite different. But it's purely because of the rules we spelled out earlier, right? So usually when you have functions that are implemented differently, Agda is just giving up. It's like, I have no clue how this could, how these two functions could be compared. You need to convince me like another way. But here what we're doing is that we're declaring two functions are equal. And then through eta for function, it's the same as saying that the two lambdas whose bodies are these functions applied to some arguments are equal. Okay, so it's expanding on both sides. And now it's actually reverting back to this sort of thing, right? You have a lambda on each side, and underneath you have expressions that are of pair type.
Yeah.
Which means that it's able to do a little bit of extension, computation, everything just in time, and these things come together.
So the algorithm for testing when two things are considered equal by the system is type directed. So when it sees that the type is a function type, what it does is it makes up a new variable with a new name of the input type and just sees what happens if you feed this variable as an input to the function. And then, looks at the output type here. Oh, it's a pair type. Well, I'm going to compare those field by field. So it's combining both of those methods.
Yeah, so you can spell it out if you want. This will also be revision for equational reasoning. Oops. So these steps are the steps that are true just by conversion. And there's a bunch of them, I suppose.
Let's see how we do.
Begin. I need to begin at some points. Propositional. Okay. So we're starting from swap composed with swap. Maybe I can just use, yeah, okay, that's good enough. So that's equivalent to this thing. Well, I don't need the, okay, which itself is equivalent to I don't know why I keep wanting to put parens on the outsides. So composition, if you remember, is defined by first applying the second function to the argument and then applying the other one to the results. And then, as we've seen earlier, so I need some extra cases still.
Yeah, there's more steps to go.
Whoop.
Yeah.
Ugh. I usually just copy paste these things. So we've seen just above, well, just out of screen, that this is equivalent to just the function itself, right? Ooh. To the pair itself, yes. And then by definition, this is just identity. And I actually introduced an extra step now.
Yeah, this between line 250 and line 251, it really is using their equal component-wise.
Yeah. Okay. All right. So now, well, we did discuss the law of excluded middle a little bit yesterday, but maybe we can look at it some more. So as I was saying, when I define OR, usually in classical logic, you have an extra rule telling you that for any set, you can decide whether it is inhabited or not. And we call this the law of excluded middle. So I'm going to write it like this on purpose. So if I have a set A, I should be able to say that either A or not, okay, using our current definitions. Okay? And we've seen that this is not provable, because if you were to attempt to prove this, LMA, then immediately you have to produce a bit of information, but you have no idea what that bit of information is. However, we can...
And in particular, you've got no way to find out what A is, so no way to say what that bit should be. But this is a much weaker statement to say, well, the law of the excluded middle might not be true, but maybe it's not false.
Right. If we're able to prove this instead, then we would be what we call anti-classical, because it would mean that it's just impossible for LAM to be true. So we couldn't even extend our current setup with the assumption that LAM holds. But the fact that we're able to actually prove not LAM is that even though it's not a statement you can prove internally, you can still prove that it's somewhat compatible with the theory. Like, the theory does not disprove it.
Yeah. Yeah. So let's do it.
So of course, the wrong move here is to use, why am I jumping around? Double negation elimination, because then you have to prove the thing straight away. So let's not do that.
Yeah.
Instead, we can normalize a little bit, and we can see it's a function, right? So let's assume that we have the negation of LM.
Right. Okay. So the way we haven't rehearsed this, but the good version of the game is that we take turns. One of us is the person. You're going to be the person who's in charge when the goal is false.
Okay.
And then you throw stuff at me. You're right. You give me the trickier problems. Right. So the thing is, when you've got an assumption that says something is false, that gives you a superpower. That gives you the ability to say, I don't like this goal, I'd rather prove that. You say, I don't like what you're asking me to do, I would rather blow up the world by proving A or not A. Okay?
Which is exactly what I'm going to do.
Yeah.
I mean, there's not very much I can do,
We
right?
definitely do not like the goal false, yes?
So
get me out of here, I'll try anything.
Yeah. So let's try to use a one assumption that actually returns false, the negation of LM.
Right.
Okay, so now I'm back to you having to
Right.
prove the law of excluded middle.
Yeah.
That's a bit
Okay.
annoying.
Now it's my go.
Oh, okay.
Yes,
Yeah.
because it's
Oh,
the goal's not
well,
false. Right. Okay. So
please
I
be
have
careful.
I have to prove A or not A. I've got absolutely no idea how to prove A, but I can at least start. I know how to start proving not A. So I'm going to go right. Okay? So now I have to prove not A. And I'm going to say, well, I know at least that's going to begin by assuming A. And now I'm back in the situation where I have to prove false, which means it's your go.
Yeah, I don't like that. So I'm gonna use the one thing that gives me a proof of false. Oh, if I can get the keyboard right. Oh, there we go. So I'm gonna call back to LAM, and now we're back to proving LAM.
Yeah,
It looks
see?
like we're running around in circles.
Yeah, you know, not here again, except that I'm better equipped than I was last time. This time I think I'll go left. But now, this time, I've still got the proof of A that I picked up when I was trying to prove not A. So I'm done. So that's the thing, is that what makes classical logic, what makes the law, what makes classical logic special is that it's a kind of time travel. It's or in another sort of sense, when I see a goal that's at OR in classical logic, I can try to play both games at once, you know, because I only have to win at one of them. And what's more, if somebody gives me stuff in one branch of the proof, I can use it in another branch of the proof. It does look awfully like cheating, because it is. I mean, that's, you know, this time travel is what is magically non-computational about classical logic. Classical logic doesn't treat time as a thing. Classical logic is God's logic, looking at the entirety of space-time and knowing everything, right? We don't get to do that. When we mere machines, you know.
We do precisely when we're double negating a statement.
Yes.
Because then we have this extra power due to the fact that, I mean, if you think about it, right, this is proving that something is impossible. So it's only useful for dismissing branches that are not very interesting computationally. But there is a general result that says that using this kind of double negation encoding, you can actually transform any statement in classical logic and recover it in this constructive setting.
Yeah.
Because that double negation gives you the ability to jump like around in your assumptions.
Yeah. So the double negation is a way of saying, of recovering that that classical logic works, but not in a way that is computationally useful. So it's a reasonable, it's the compromise that we can explain properly.
And here you have a prompt to play similar games to prove that if you assume the law of excluded middle, you can prove double negation elimination. And the other way around also.
There's a bunch of variations on this. I guess the other thing that is worth mentioning, unless it's coming up. Yes, De Morgan is coming up.
Yeah.
Yeah.
So I think that's next week.
Okay, fine. But yes, think about this in terms of where the bits are, right? When you learned this in first year, right? But now pay attention. Where are the bits in this picture? Okie dokie. Looks like a good place to call it.